Alright, let's go deeper into state machine synthesis. And I'm going to work with a different state diagram here, which is going to be a simple counter. So I'm not going to have um, 4 states, I'm going to actually have 3 states. And let's call these states A, B, C. And let's set up our state transitions so that we have a single input, and if the input is a 1, we will move from one state to the next, and when we get to state C, we'll come back to the beginning. And if our input is a 0, we'll stay in whatever our current state is. And let's just have a more machine, so we'll make our output 0 in states A and B and 1 in state C. And let's design this using each of the 3 types of flip-flops that we commonly work with, D, T, and JK. And when we're setting up our state transition table, the big wide table, we can reuse a lot of that as we move to other kinds of flip-flops. So let's start off with this diagram, and let's begin with deciding how many states we have. Well, we have 3 states. We're going to use 2 flip-flops, and we'll start with D flip-flops, and then we'll do T, and then we'll do JK. And so let's make a state assignment table. So state name, and if we got 2 flip-flops, we have 2 outputs, Q1 and Q0. So our states are A, B, and C, and I'm just going to set up, kind of arbitrarily, our 3 states to be this: 0, 0, 0, 1, and 1, 0. Alright, so let's make our state transition table. So we have 1 input, X, and we have 3 states of interest. But we have 2 flip-flops, so we actually have 8 combinations of flip-flop outputs and our input X. So present state and our input X. So we can be in A with a 0, A with a 1, B with a 0, B with a 1, C with a 0, C with a 1. And let me list the values of Q1, Q0. So for an A, these are both 0. For state B, these are 0, 1. And for state C, these are 1, 0. And I'm going to note in here that there is another pair of possibilities. Q1 and Q0 could both be 1s, and our input could be a 0 or a 1. And we don't have a name for this state. And this is going to introduce some don't cares into our truth table, because we're going to assume we're never in a state where Q1 and Q0 are both 1s. So if we're in that state and our input is a 0, we don't care what the machine does. If we're in that state and the input is a 1, we don't care what the machine does. So we're going to have some don't cares available to us. Alright, so let's go ahead and add our output column. And our output is just, shown in each of our 3 states. So in states A and B, the output is a 0. And in state C, the output is a 1. And if we're in this 4th ill-defined state, we don't care what the output is. Our circuit could make it a 0 or a 1. Doesn't matter to us. Okay, so now let's write down what our next state should be. And so if our input is a 0, our next state is the same as our present state. So if we're in A and we get a 0, we stay in A. B stays in B. C stays in C. If our input's a 1, A should go to B. B should go to C. C should go to A. And here again, if we happen to be in the state where both flip-flops are 1, we don't care what the next state is. So now let's write down what the next state is in terms of Q1 and Q0. So I'll label these Q1 plus, Q0 plus, like the heading in, a flip-flop table. And, state A, both of these should be 0. State B, these should be a 0, 1. And state C, they should be a 1, 0. And since we don't care what state we're in these last two cases, it doesn't matter to us what Q1 and Q0 are. All right, so this part of our state table completely ignores the question of what kinds of flip-flops we have. This is only looking at present state, input, output, next state. So suppose we have D flip-flops. So we're going to have D1, D0. Well, remember, D flip-flops are the simplest to analyze. If we want a D flip-flop to output a 0, we should set the input to 0. If we want a D flip-flop to output a 1, we should set the D input to 1. And if we don't care what the D flip-flop outputs, it doesn't matter what we set the D input to. So in this case, that's what our D outputs look like. All right, now if we have T flip-flops, toggle flip-flops, we can't just look at what we want the flip-flop to be. We have to look at what it currently is. If it's currently a 0 and we want it to stay a 0, then the toggle input should be 0. And in fact, if the desired state is the same as the current state, our toggle input should be a 0. 0 goes to a 0, that's a 0. But here it's currently a 0 and we want it to become a 1, we should toggle. Here it's a 1, it should stay a 1, don't toggle. Here's a 1, we want it to become a 0, so we'll say toggle. And whether it's, currently a 1 or not, we don't care what the next state is. Doesn't matter what the T input is. All right, T0, we're looking at Q0 and Q0 plus. Same value, don't toggle. Opposite values, toggle. Don't toggle, toggle. And then these two, it's currently a 0 and we want the new state to be a 0, so don't toggle. Then we don't care what goes in there. All right, JK flip-flops. All right, so let's do this in the most straightforward way possible, and then we'll complicate it. Well, no, let's just complicate it up front. All right, so let's look at this first entry here. Q1 is a 0, and we want the new value of Q1 to be a 0. So we want Q to be unchanged. Now let's look at a JK flip-flops transition table. So if J and K are both 0, Q is unchanged. If our inputs are 0, 1, it becomes a 0, 1, 0 becomes a 1, and 1, 1 toggles. All right, so in this first entry, Q1 is a 0, and after the clock tick, we want it to remain a 0. There are two ways to achieve that. We could say set J and K equal to 0, 0, because that says don't change. Or we could set J and K equal to 0, 1, which says set the output to a 0. So we could have either 0, 0 or 0, 1. Well, we can write that by saying J1 should be a 0 and K1 doesn't matter. Okay, so let's think about this a little more. Why is K1 a don't care? Because if J1 is 0 and K1 is 0, this flip-flop will stay unchanged, and since it's currently got a value of 0, after the next clock tick, it will still have a value of 0. But if our circuitry happens to set K1 to a 1, this flip-flop has a 0, 1 coming in, which says after the next clock tick, set the output to 0, which is what we want. And the same thing in this second row. We currently have a 0. We want the output to become a 0. we can set JK to be 0 and don't care. And the same thing in this third row, currently a 0, we want the output to be a 0, that's a 0 and a don't care. But in this fourth row, the flip-flop's currently outputting a 0, we want it to output a 1. So we want that 0 to change to a 1. Well, there's two ways to do that. One way is to set JK equal to 1, 0, because that says set the output to 1. But another way is to set JK to 1, 1, because that says toggle the output, which will change that 0 into a 1. So as long as J is a 1, it doesn't matter what the value of K is. So in this case, we can set J to 1 and K doesn't matter. Alright, so that's where these don't cares are coming from. But we don't want to have to keep doing this analysis. So there's a different kind of table we can make, especially for a JK flip-flop. And it looks like this. If the current value is Q, and we want the next value to be Q plus, what should we set J and K to? Alright, well we already saw if Q is 0 and we want the new value to be 0, we should set J to 0 and K doesn't matter. If the current value is 0 and we want the new value to be 1, we should set J to 1 and K doesn't matter. So what if the current value is a 1 and we want the new value to be 0? Well, there's two ways to do that. Set JK to 0, 1, which says clear the output, or set JK to 1, 1, which says toggle the output. Change that 1 to a 0. So J can be anything, K has to be 1. So this is a don't care and a 1. And the last case, we currently have a 1 and we want it to stay a 1. So there's two possibilities. We could set J and K to 0, which says don't change anything. Or we could set J and K to 1, 0, which says set the output to 1. So J doesn't matter as long as K is 0. So this is sometimes called an input excitation table. And this is a shortcut that tells us if we know the current output of the flip-flop and we know what we want the new value of the flip-flop to be, here's how we set up J and K. And once we have this table, we can pretty quickly fill in this transition table. So let's fill in the rest of the J's and K's. We want to go from a 1 to a 1. That's a dash 0. Here we want to go from a 1 to a 0. That's a dash 1. And these we don't care about. And then if we look at Q0, we're going from a 0 to a 0. That's a 0 dash. 0 to a 1. That's a 1 dash. 1 to a 1. That's a dash 0. 1 to a 0. That's a dash 1. 0 to 0. That's our 0 dash. 0 to 0 is 0 dash. And we don't care about these last two rows. Alright, so there's a complete state transition table for all three types of flip-flops. D flip-flops, T flip-flops, and JK flip-flops. And so now we have to go ahead and we have to write equations. And this is an exercise in making K-maps, right? So let's just do a K-map for J1. All right, so J1. And we'll make our usual setup. We'll put Q1, Q0 here, and our input X over here. And it looks like we have a 1 in the case where our input is 0, 1, and X is a 1. So we're 0, 1, 1. That's a 1. And it looks like we have don't cares when our input for Q1, Q0 is 1, 0, or 1, 1. So all of these our don't cares. And then everything else is a 0. All right, well, if we try to cover this with rectangles, we can get a nice 2x1 covering right here. That covers the 1. We're not going to worry about the other dashes. And the equation for this is J1 equals, Q1 doesn't matter, Q0 has to be a 1, and X has to be a 1. So J1 just comes from an AND gate, right? Just take the current output of flip-flop 0, AND it with your input X. That gives us J1. And we can see, for example, that down here, Q0 ANDed with 1, this J input's going to be a 1. Doesn't matter. Up here, Q0 ANDed with X, this J input's going to be a 0, but that doesn't matter. All right, so we do this, you know, to find J1, K1, J0, K0 if we're using JK flip-flops, or other things for D flip-flops, or T flip-flops, and then we go ahead and we build a circuit. All right, so that's another example, starting with, you know, this diagram, and heading up to, you know, a series of equations from which we would sketch the circuit diagram. So one of the takeaways here is, you know, this idea of using these don't cares when we have JK flip-flops, because there's multiple ways we can achieve a desired output, right? So we can use this excitation table to say if we want to go from here to here, that's what the value of J and K should be. Now we can do this for other flip-flops as well, right? We could say if we have a current value Q and we want to go to a value Q plus, what should our toggle input be? Well, if it's a 0 and we want to go to a 0, don't toggle. If it's a 1, we want to go to a 1, don't toggle. If it's a 0 and we want to switch to a 1, or a 1 and we want to switch to a 0, toggle, right? But a toggle flip-flop is simple enough that you know, if we're filling out our table and we see, oh, here Q0 is a 1 and we want the new Q0 to be a 0, okay, well, we should toggle. We can just write that in. But for JKs, this is particularly useful because of the don't cares. And, you know, the more don't cares we have, generally the simpler our equations are, which means the simpler our circuit's going to be to draw and to build and to test. All right. The other thing I want to just mention on here is that, you know, we said we don't really care what happens if your flip-flops end up in this state because we don't expect them to. We expect this machine to only go through these states. But what if when we power up the system, it just happens that both of our flip-flops are outputting 1s? And what if the way that we end up filling in these don't cares, it just so happens that if our flip-flops are outputting 1s, they continue to output 1s? Right? We might power up our system and find that it's in this ill-defined 4th state and it never leaves there. So when we actually sketch the circuitry for this is where we can take advantage of things like an asynchronous clear input. So we might have our 2 flip-flops, and there might be this clear input on the bottom, and we might take those clear inputs and feed them into some kind of reset signal. And when we first power up the system, we might put a little pulse on this reset line. And we can build circuits so when power is first applied, it generates a pulse, right? A 555 timer is a good way to do that. And then that would force all of our flip-flops to go to a state where they're outputting 0s. And that would basically put us in state A. And so when the system first gets power, it goes into a known state. And so that's a pretty common thing, right? Rather than designing for all possible combinations of flip-flops, just put in a reset circuit that initializes the system to a known configuration. So that would be a useful embellishment. All right, the other thing I want to mention, just for completeness, is that when we sketch these circuits, we don't usually draw the clock. But, you know, we would put a little signal here showing that, you know, these are clock clock devices edge triggered, and we could, you know, typically just go ahead and tie those together, feed it from a clock line. But this should be just, you know, a wire. It just goes directly to the clock, no gating or anything like that. And notice that in this circuit, what we did was we came up with a way to effectively stop the clock. If you take your input X and you set it to a 0, it's as if the clock has stopped. Because, you know, each time that the clock ticks, we just stay in the current state. But rather than taking, you know, an input and ANDing it with the clock to actually stop clocking these devices, we design the machine so that it continues to receive the same regular clock ticks, but we control what it does so that when our input X is 0, it stays in the current state. Right? So that's back to this idea of don't gate the clocks, don't monkey with the clocks, just feed them to all of your devices exactly the same, but design your circuit with the ability to do things like ignore the clocks or modify what happens when a clock ticks. All right, so one more example, which we will do next time, which is looking at a different way of coding states using what's called one-hot encoding, and that's going to be a case where we decide that, you know, we have 4 states, but maybe we're going to use 4 flip-flops instead of 2. So we'll go through that really quickly in a separate video, and then that's going to do it for state machine synthesis. And that'll take us into our next topic, which will be Verilog.